Our group topic is about Wi-Fi 6, and I will introduce technological innovations and the socio-economic impacts of Wi-Fi 6. Topic 1. First part is introduction and background. For historical context, Wi-Fi technology has evolved significantly over the years to meet the increasing demands for higher speed, lower latency, and improved efficiency. The transition from Wi-Fi 4 to Wi-Fi 5 and ultimately to Wi-Fi 6 reflects the growing need for better wireless performance, especially in dense environments with multiple connected devices. For overview, Wi-Fi 6, based on IEEE standard, is the latest generation of Wi-Fi technology. It is engineered to deliver higher throughput, improved spectral efficiency, and lower latency compared to its predecessors. By incorporating advanced features like orthogonal frequency division multiple access, enhanced multi-user multiple input, multiple output, 10 and 24 QAM modulation, and TWT. Wi-Fi 6 is designed to meet the increasing demands of modern digital environments. Topic 2. This part is technical specifications for frequency bands. Wi-Fi 6 operates in the traditional 2.4 GHz and 5 GHz frequency bands, providing better backward compatibility, improving performance. For modulation techniques, Wi-Fi 6 employs 10 and 24 QAM, which increases the amount of data transmitted per symbol compared to Wi-Fi 5's 256 QAM. For channel widths and aggregations, Wi-Fi 6 supports flexible channel width to optimize bandwidth utilization and performance. Number 1 for 20 MHz standard bandwidth for 2.4 GHz and 5 GHz bands. Number 2 for 40 MHz used primarily in 5 GHz band, supporting higher speeds. Number 3 for 18 MHz provides higher throughput, common in high-speed applications. Number 4 for 160 MHz maximum supported bandwidth, ideal for high-performance use cases. For data rates and throughput improvements, Wi-Fi 6 significantly enhances network performance by increasing data rates and overall throughput, achieving theoretical maximum speeds of up to 9.6 GHz, far exceeding the roughly 3.5 GHz offered by Wi-Fi 5. Topic 3. This part is key technologies for orthogonal frequency divisions multiple access. Wi-Fi 6 utilizes OFDMA to enhance efficiency in high-density environments. Instead of waiting for one device to finish transmitting before another begins, OFDMA splits the available channel into smaller subchannels called resources units. Each RU can be independently allocated to different devices, allowing simultaneous transmissions. This division significantly reduces latency and improves overall network capacity, especially when multiple devices are connected. For multi-user MIMO, one of the notable improvements in Wi-Fi 6 is the advancement of MU-MIMO technology. Earlier standards like Wi-Fi 5 primarily supported MU-MIMO in the downlink, meaning the router could only send data to multiple devices simultaneously. Wi-Fi 6 expands this capability by supporting MU-MIMO for both uplink and downlink transmissions. Additionally, it supports more spatial streams, allowing even more devices to communicate concurrently. This results in higher throughput and improved performance in environments with many connected devices. For target wake time, TWT is a critical innovation in Wi-Fi 6 designed to optimize power consumption. TWT schedules specific times for devices to wake up and exchange data, which means that devices, especially battery-powered IoT gadgets, can remain in sleep mode for longer periods. By reducing the frequency of idle listening, TWT extends battery life, making it especially beneficial for devices where power efficiency is paramount. For higher order modulation, Wi-Fi 6 employs 10 and 24 QAM to increase the data rate. In simple terms, higher order modulation schemes allow each symbol transmitted to carry more bits of information, compared to 256 QAM used in previous standards. 10 and 24 QAM can encode 20% more data in the same time frame when the signal quality is good. This enhancement directly translates into higher throughput and improved network performance in optimal conditions. For basic service set, BSS coloring is a novel technique introduced in Wi-Fi 6 to mitigate interference in dense network environments. By assigning a unique color or identifier to each BSS, devices can easily distinguish between transmissions originating from their own network and those from neighboring networks. This differentiation enables devices to ignore signals from other BSS that are not relevant, thereby reducing the likelihood of collisions and improving overall spectral efficiency. For beamforming, improved beamforming techniques in Wi-Fi 6 leverage advanced algorithms to precisely steer and focus radio frequency energy toward connected devices, significantly enhancing signal quality and reducing interference. This dynamic approach allows access points to adapt to their beam patterns in real time, overcoming obstacles and mitigating multiple paths fading, which is especially beneficial in dense and complex indoor environments. For new frequency bands in Wi-Fi 6E, it extends Wi-Fi 6 capabilities by introducing the 6 GHz frequency band in addition to the traditional 2.4 GHz and 5 GHz bands. The 6 GHz band offers a wider spectrum with larger contiguous channels and experiences less interference from legacy devices. This expansion not only alleviates congestion, but also paves the way for higher data rates and improved reliability in crowded environments. Topic 4 is about physical layer, OFDMA. For a brief introduction, OFDM working mode. On the left, users are differentiated by time. Each time segment, the user fully occupies all the sub-carriers and sends a complete packet. OFDMA working mode on the right picture is that users are distinguished according to the time frequency resources, block RU. We first divide the resources of the whole channel into a small fixed size time frequency resources block, which is also called RU, resources unit. In this mode, the user's data is carried on each RU. So from the perspective of the total time frequency resources, there may be multiple users sending at the same time on each time slice. OFDMA generally has two advantages over OFDM. Number one, a more nuanced allocation of resources, especially in the case that the channel state of some nodes is not very good. The channel time frequency resources can be more finely allocated according to the idea of the water flood theory. That is, the transmission power can be allocated according to the channel quality. Number two, can provide better QoS because the initial 202.11 occupies the entire channel. If a QoS packet needs to be sent, it must wait for the previous sender to release the entire channel, so there will be a long delay. In the case of OFDMA, because one sender occupies only part of the channel, the delays of QoS node access can be reduced. For RU, in 802.11ax, one of the smallest time frequency units is RU. RU is a relative concept. For example, there are many different sizes of RU, as shown in the picture below. OFDMA subdivides the channel into smaller resource units RU. With OFDMA's resource segmentation, multiple clients can transmit in parallel by occupying different RU resources. A 20 MHz OFDMA channel consists of 256 subcarriers. These subcarriers make up a number of subchannels we call a subchannel RU. The AP of 802.11ax determines how many RU can be used within a 20 million Hz channel and the different combination of RU flows. 802.11ax AP can allocate the entire channel to a client and can also use OFDM technology to allocate the channel to multiple terminals at the same time. In order to be compatible with other earlier 802.11 protocols, in 802.11ax, the management frame and the control frame will still use 802.11a or zhaowen or AC OFDM technology and will be transmitted at the basic transfer rate, which ensures that other early 802.11 terminals can understand each other. At this time, both the management frame and the control frame are transmitted using the entire 20 million Hz channel and the entire 64 subcarriers. OFDM technology is only used for data-free interaction between 802.11ax APs and 802.11ax terminals. And for OFDM and OFDMA subcarriers, as shown in the figure above, a 20 million Hz channel in 802.11n or AC consists of 64 subcarriers, each OFDM subcarrier being 322.5 kHz. 52 subcarriers are used to carry data subcarriers. 4 are used as parallel subcarriers, and 8 are used as unused subcarriers. So OFDM subcarriers can be called OFDM subcarriers of OFDM towns. 802.11ax introduces a longer OFDM symbol time, 20.8 US, which is 4 times longer than the traditional OFDM symbol time, 3.2 US. The subcarrier interval is numerically equal to the reciprocal of the OFDM symbol. As the OFDM symbol becomes longer, the single subcarrier bandwidth or subcarrier interval is refined from 312.5 kHz to 78.125 kHz. Narrower subcarrier intervals allow for higher frequency domain resolution, improved equalization, and increased channel robustness. In 802.11ax OFDM, there are 3 types of subcarriers as follows. Number 1 is called data subcarriers. These subcarriers are used to carry data, and their transmission rates are on 802.11 AC MCS, with the introduction of 2 new MCS, modulation and encoding schemes, including a higher modulation order of 10 and 24 QAM. Number 2 is called pilot subcarrier. This kind of pilot subcarrier is used for synchronization between the sender and the receiver, and does not carry modulation data. Number 3 is called unused subcarriers. These subcarriers are mainly used as guard subcarriers or more subcarriers to resist interference from adjacent channels or adjacent subchannels. For example, resist ICI. Topic 5 is about performance improvements. For latency reduction mechanism, Wi-Fi 6 introduces key changes that dramatically cut down on transmission delays. For example, the integration of OFDMA enables the access point AP to assign subchannels. This called resource unites on RUs to multiple devices, so that several transmissions occur simultaneously. This centralized scheduling minimizes contention and the delays associated with traditional CSNA or CA-based channel access. In addition, features like target wake-time TWT help synchronize transmissions and allow devices to switch between scheduled communication slots, reducing the latency impact during network access and helping in low-power scenarios. These innovations can reduce channel access delays, which is critical for latency-sensitive applications. For comparisons with Wi-Fi 5, where the maximum theoretical data rate improvement of Wi-Fi 6 over Wi-Fi 5 is around about 37 to 39%. The practical throughput benefits are even more pronounced in real-world networks. In dense environments and multiple client scenarios, Wi-Fi 6 can achieve up to 4 times the throughput per user compared to Wi-Fi 5. For performance in high-density environments, dense settings such as airports, stadiums, and large offices, place unique demands on wireless networks. Wi-Fi 6 is specifically designed to address these challenges. For testing and benchmarking, initial real-world studies have validated the theoretical advantages of Wi-Fi 6. Testbeds using commercial Wi-Fi 6 routers and ground devices have shown 1. A significant reduction in latency when coexisting with legacy networks. 2. Throughput means that on the dense client nodes can reach triple to 4 times compared to Wi-Fi 5. especially in scenarios with short latency sensitive transmissions. 3. A noticeable improvement in performance consistency with lower packet collision rates and better overall spectrum efficiency. That's all attention. Thank you for your attention.